So now let's ask about something. Pretty often when we go through things, I'll say try this at home. This is probably something I wouldn't recommend trying at home. So let's ask what happens if you connect a wire, an ideal wire, so it has no resistance, straight up across the terminals of a battery. So imagine you have a battery, it's got a plus terminal and a minus terminal, and you just put wires over those terminals. So then what happens in that situation? If we look at our circuit diagram, when we connect a battery, it does have some internal resistance and it drives a current through the circuit. So that's what happens in the thing. If you don't have any appreciable resistance, what you get is called a short circuit. So that's what happens if you don't have much resistance in a circuit, either external resistance, internal resistance, or wire resistance. So let's kind of think about what does that mean in terms of current. If we apply Kirchhoff's voltage law around this circuit, when we write that law, we would have our potential increase epsilon minus our drop over the internal resistance, and that equals 0. That would give us a current I equals the potential divided by the resistance R. If that resistance R is small, then what happens is that our current is big. So if you just have a little 1.5 volt battery at home, your current is not going to get that big. It's not going to be that big of a deal because there is some internal resistance in that battery. However, if we get closer to an ideal battery, then that resistance approaches 0 and the current will approach infinity. What's going to happen here is it's going to get hot, it's probably going to spark, and it may catch fire. If you did this to a car battery, especially one that was in good shape with a low internal resistance, it could actually explode. So in general, you don't want to have short circuits. Next, let's get to talking about devices I've used on the FET simulations without discussing them, and those are devices that we use to measure current and potential. The device we use to measure current is called an ammeter. That's got a circuit element symbol of an A inside of a circle, and then that connects to wires, of course. So that's what an ammeter looks like when we write it in a circuit. So if we have a simple circuit like the one I have on the left, it has a source of potential, it has some sort of external resistance, and it draws a current I. These kind of problems, we can write down Kirchhoff's loop rule, which has a potential increase due to the battery and a potential drop across the resistor equals 0. And in this kind of a circuit, we could certainly calculate the current I is the potential divided by the resistance. That's pretty familiar with us for right now. We've done that a bunch. But what if we wanted to measure the current with a device with an ammeter? First thing we have to do is we have to ask a couple of questions. One good question is, how do we put an ammeter in our circuit? Where should it go? What should the connection be like? Well, we want the ammeter to measure the current through our resistor. If we want it to measure the current, we want it to have the same current, so it has to have a series connection. Okay, so anytime you want to measure current, your ammeter has to be in series so that it has the same current. If you want to think ahead, you might start to wonder about how a voltmeter would have to be connected. Okay, so that's one thing. We know it's going to have to be connected in series, and that's what we've got drawn in our picture on the right. We go from the battery to the ammeter into the resistor. So the current I comes out of the battery, goes through the ammeter, goes down through the resistor. All of those things have exactly the same current I. Okay, what feature does the ammeter have to have? So an ammeter is a real device, so it is going to have some resistance. I'm going to label that R with an A for resistance of the ammeter. And I'll call this R go with our 6 ohms. That'll just be the resistance, the external resistance in the circuit. How about this RA here? Do we know anything about what that should be? Well, let's write down our Kirchhoff's current law, or our Kirchhoff's potential law for this circuit. We've got an increase due to the battery. We've got a drop over the ammeter. And we've got a drop over our external resistor. If we wish, we can rearrange this as an expression for our current. It's going to be the potential divided by RA plus R. If you look at this equation, if you want to measure the current, and if you want both of our circuits on the left and right to draw about the same current, you don't want the ammeter to affect the whole circuit. You want the ammeter to be pretty much invisible. In order to have that happen, the resistance of the ammeter has to be very small. Okay, so RA is small. Otherwise, it's going to change the current I. So you don't want ammeters and voltmeters to change your circuits just by adding them. That's why you have to think carefully about what the currents are. Okay, so that tells us about ammeters. Next, we'll talk about how to measure potential. Maybe just before we get started on voltmeters, we can actually do an ammeter example. So let's say we have a circuit like the one we have drawn here, and the ammeter reads 3 amps. I'm going to label the current going through the ammeter as to the right, and it equals 3 amps. Okay, we want to find I1, I2, and epsilon. This is going to be a Kirchhoff's law problem, so we're going to have to think about the current law and the potential law. Let's go ahead and write down our current law. So I'm going to pick my junction in the middle on the right. So my current law tells me that the net current in, that's I1 plus I3, equals the net current out, I2. I3 is easy, that's 3 amps. We're going to need I1 before we can go ahead and solve I2. So let's do a loop rule. I'll take one of my loops to be around the top part of the circuit. So this is my loop 1. Let's get careful with my signs here. So my current I1 goes through the 3 ohm resistor from left to right, so positive to negative. My current I3 goes through the 2 ohm resistor from left to right, so plus to minus. This will help us when we write down our loop rule. So for loop 1, we've got a potential increase due to our battery, plus 9 volts. We've got a drop over our 3 ohm resistor, so minus 3I1. The ammeter has a very tiny resistance, so we say there's no potential drop over the resistor. And then for our no potential drop over the ammeter, for our 2 ohm resistor, our loop and our current are going in opposite directions, so that's a potential increase. Or our loop goes from plus to minus, or from minus to plus, so that's an increase. So we have plus 2 times I3 equals 0. We know our I3, that equals 3 amps, so we're all set to find I1. So 9 minus 3I1 plus 2 times 3, that's 6, equals 0. 9 plus 6 is 15, equals 3I1. I1 is 15 over 3, or 5 amps. So there's my current I1. Now that I've got I1, I can come back to my current law and find I2. I2 equals I1 plus I3 equals 5 amps plus 3 amps equals 8 amps. Okay, that's the two currents found. Now I want to find the potential of the unknown battery. So what is epsilon? Let's write another loop rule. I'm going to take the whole outer loop here now for that second loop. So this is going to be my loop 2. I'm going to label in my plus and minuses here. So for my 9 volt, it's labeled. My 3 ohm, it's labeled. My epsilon is labeled. The last one I need to label is my 1 ohm. So my current I2 comes down, then goes from right to left and makes this end positive and this end negative. Okay, next I'll write my loop 2 rule. My loop 2 rule has got a potential increase due to my battery, a drop over my 3 ohm resistor. Okay, for my battery, I go from negative to positive. That's an increase due to that battery, and then I have a drop over the 1 ohm resistor. That all sums to give me 0. In this equation, I know I1, so I've got minus 3 times 3, that's 9, plus epsilon minus 1 times I2 is 8, equals 0. So this tells me that my epsilon, the potential of that battery, is equal to 8 volts.